I'm going to start with a classic trick today. I got some dishes on the table, on a tablecloth, and if I take the tablecloth, you give it a sharp snap, I can pull it out from under the dishes. How does it work? It's not a question of magic, it's a question of physics, as we'll see. Here's the problem. It's possible to whisk a tablecloth from under a set of dishes with minimal motion of the dishes by making a very rapid pull of very slippery fabric that makes a very small friction force. Draw a free body diagram for a dish on a tablecloth being pulled to the right and explain why, for a rapid tug, the motion of the dishes is so small. So we're going to look at why this is a physics question and not a magic question. Let's take a look at the problem and see what we're being asked to do. First, we're going to draw a free body diagram of the dish on a tablecloth being pulled to the right, and that's going to be important. It's pulled to the right. And ultimately, we have to do this. We have to explain why, for a rapid tug, the motion of the dish is so small. That's what we're looking to explain. Now, let's look at the pieces in the problem statement that are going to be important for us. There's a couple of things that are brought up. First off is this. It's a rapid pull. Okay? That's going to be important for our solution. The other piece is this. It's very slippery fabric. And the reason why slippery fabric is important is because it makes a small friction force. Those are pieces that we're going to use in our solution. And this is our preparation step. We've gone ahead and taken a look at the problem. We found the interesting pieces which we need to consider. And for this problem, the solution is actually drawing the picture, drawing the free body diagram. So let's do that. All right, now we're going to draw the free body diagram. First off, let me draw a physical picture of the situation. Here's a table, and there's a tablecloth like so, which goes over the edge, and there's a dish sitting on top of the tablecloth. And the tablecloth is going to be pulled to the right. Now, let's draw a free body diagram for this situation. Here's the dish. Let's think about the forces that are at work on it. Well, there's the weight force, which acts downward, always true. There's an upward force as well. There's an upward normal force. And the weight force and the normal force are going to be equal to each other because there's no vertical motion. So we can say that that's true. Now let's think about the friction force. Because there is going to be a friction force. The whole reason why the dishes will tend to slide is because of that friction force. What's the direction of the friction force? We'll give you some choices. We know the tablecloth is sliding. And so this is kinetic friction. And kinetic friction opposes motion. Look at the dish on the tablecloth. The tablecloth is moving to the right. The dish is staying essentially stationary. So that means from the point of view of the tablecloth, the dish is moving to the left. And so the friction force opposes that. The friction force goes to the right. And it's kinetic friction. And that makes sense because if the friction force was really large, we know which way the dish would move. It would move in the same direction as the tablecloth. It would move to the right. There's one last piece of the puzzle which we have to answer here, and that's this. What is the direction of the net force? And what is the magnitude of the net force equal to? We'll give you some choices. We said that the weight force and the normal force were equal to each other, and that's because there's no vertical motion. So the weight force, the normal force, will cancel each other. Then the only force that remains is the friction force. And so the net force, and that's the most important thing in this problem, the net force is just equal to the friction force. And the direction of the net force is to the right, in the direction of motion of the tablecloth. Now there's one more piece of the puzzle, and that's this. Why don't the dishes move very far? These are the forces that act on the dishes, but why don't they move very far? Let's take a look at Newton's second law. And Newton's second law is the acceleration is equal to force divided by mass. But remember, the force that appears in here in Newton's second law is the net force. But the net force in this case is just the friction force. And we know something about the friction force. We know the friction force is small. So if the friction force is small, that tells us that the acceleration is small. We also know this. When we pull the tablecloth, there is going to be an acceleration. The acceleration is going to cause a change in velocity of the dishes, but we want that to be small. And so what we do, and we were told this, is we pull the cloth very rapidly. What that means is the time interval is very small. The time that the friction force does its work is really small. So I have a small acceleration, I have a small change in time, and the net result is the change in velocity of the dishes is very small. So a very small change in velocity and a very small time, they don't go very far. And that is ultimately the physics of how this works. Let's assess our result. For the assessment, I'm going to show you how to set up and actually do this. Here's my tablecloth. It's a piece of very attractive polyester fabric from the 1970s. And the reason I chose that is because it's very, very slippery. And what that means is very little friction. If I take a glass and slide it, it goes some distance. Whoa! It goes some distance. And that tells me not much friction. Okay, now I have my glasses. I'll put my cup here. And I need to have a very, very sharp snap. I need to move the tablecloth really quickly because we saw you have to have slippery fabric, but I also need a short time. So it's a snap. The other thing is this. Some people have a tendency to pull up, and if I pull up, it's not a friction force. It's a normal force. I'm launching these things into the air. I want the tablecloth only going sideways. And so what I do is I don't pull it out. I pull it down. When I pull it down, the tablecloth is going to go over the edge like so, and it's only moving horizontally. That's a piece that I want. The other crucial piece of the puzzle is I have a piece of fabric with no edge, so the edge is not going to hit the glasses. So I take it like this, I get set up, and I give it a snap. Now we said that the friction force is in the direction that the tablecloth is moving. It's going to be pulling the glasses this way. So they'll move, but they won't move very much. And this time, to show that, I'm going to do it again, but we're going to do it on the high-speed camera. And let's take a look at the motion. So the tablecloth starts to move to the right, but it moves very, very quickly. This is 300 frames a second, and so the motion is extremely rapid. And look at the glasses. They do move a little bit to the right in the direction of the friction force. But the force is so small, the time is so short, that they don't move very far before settling back down again on a table. And that's the physics behind this classic trick. And it's also a way of assessing that the work that we did was correct. Makes sense. Physics is about the world around us.